So it's easy to determine if a function is continuous or discontinuous from a graph. But oftentimes the graph is not given, so we need to determine continuity or discontinuity from a formula. So if a function is given with a formula, then we need to determine continuity using a special formula for continuity. Formula for continuity. Function f or f of x is continuous at point x equals a, or at x value x equals a, when the following formula holds. Limit as x approaches a f of x equals f of a. And this formula says that the limit of the function as x approaches a equals the value of the function as x equals a. So limit as x approaches a equals value as x equals a. Now this formula can be used in two different ways. If we already know that the function is continuous, which means we already know that this formula holds, then this formula can be used to actually solve the limit. Once again, this formula says that if the function is continuous, limit equals the function value. And so if we already know that the function is continuous, then we can use this formula to calculate the limit, which means we calculate limit just by plugging in. So let me write this. So this formula can be used in two ways. First way is that if we know is continuous, if somehow we know somebody told us that it's continuous, then we have an easy way of calculating limit. So what this formula says, it says that if the function is continuous, then the formula holds, and it says that the limit equals function value. So to calculate the limit, we just need to plug in. And we already used this method of just plug in pretty often. We didn't mention continuous functions back then, but actually this is the reason why this method worked, because the function that we dealt with were continuous. Now, how do you know that the function is continuous? How do you know that this formula can be used to actually calculate the limit? In fact, most functions that we deal with are continuous. All the functions, or most functions expressed with a single formula, are continuous, such as polynomial, exponential, trigonometric functions, ratios, square roots, etc. So how do we know that a function is continuous? Most functions that we deal with are continuous. And most functions expressed with single formula are continuous. continuous on their domains, which means at every x value or every point where they are defined. Everywhere where they are defined. For example, let's say function f of x equals, I don't know, sine of x squared minus 3 square root of x divided natural logarithm x, something like this. It is continuous everywhere it's defined, and therefore we can calculate limit of this function whenever x approaches anything by just plugging in, and that's precisely what we did to calculate limits. As long as we have a single formula, in most cases when we have a single formula, such a function is continuous, and that limit formula can be used to calculate limit of such a function. So once again, the simple use of this formula is that limit is just plug in. Limit is just plug in. But this idea only works when we already know that the function is continuous. For example, function of expressed with a single formula is continuous. And what if we don't know? Then here comes the second use of the formula. This formula can also be used to determine if a function is continuous or discontinuous. So the same formula, namely limit as x approaches a f of x equals f of a, then the function, the limit of a function equals value of the function can be used to determine continuity of a function at a point. Now you may argue that why do we need to determine continuity? We already know that all such functions are continuous, and those are the only functions we ever deal with. So it looks like every function, all the functions we deal with are continuous. Then why do we need to determine continuity if we already know the function is continuous? The trick is that if the function is expressed with a single formula, then most probably it is continuous. But some functions are determined with more than a single formula, with several formulas. So here's an example of a function determined with several formulas. So here's an example of a function where we need to check continuity. F of x equals x squared minus 3 for x greater or equal to, and x plus 1 for x smaller than 2. Now this is an example of a function that is not expressed with a single formula. It is expressed with two separate formulas, one formula for x values bigger than 2 for certain x values, and the other formula for certain other x values for smaller than 2. And because it's not a single formula, we cannot reason that this function is therefore continuous. And now the question is find any points of discontinuity. For f of x. Now how do we approach that? We definitely need to use this formula for continuity. F of limit x approaches a f of x equals f of a. And since we need to check continuity, I put question mark again. So we need to determine whether the left-hand side equals the right-hand side. And once again, if this formula holds, which means if the left-hand side equals right-hand side, then the function is continuous for this x equals a. And if it's not equal, then the function is discontinuous. So is it equal or not? How to check it? Now we may argue that there are infinitely many points to check, and so it's impossible to check them all. But here is how to check them. So let's pick one point. Pick, for example, x equals 5. So 5 is my A now. And then, using this formula, will be limit x approaches 5, f of x, that's the left hand side, equals f of 5. And again, it may be equal or not equal, so I put question mark here. We need to check if it equals or not equal. So right hand side is easy, f of 5, we just plug in because 5 is bigger than 2, so 5 squared minus 3 is 22. Left hand side is much less easy, so it's a limit, so we have to calculate this limit. But here is an approach like how we can calculate this limit. Because x approaches 5, now I want to use some method that close to numerical method. I don't really plug in, but I want to check what x values I want to plug in if I do it numerically. And those are x values like 5.1 and 5.01 and 5.201, etc. And also 4.9, 4.99, 4.39, etc. And we need to plug them all into the function value. But if you check these two formulas determining the function, plugging them all into the function to determine the value. When you do plug in all of those x values, or try to plug in, you see that all of them you will plug into the top formula because all of them are bigger than 2. And so, and the right hand side too, you only plug it into the top formula, never into the bottom formula. So what it means that in this entire calculation, both for the left hand side and for the right hand side, the entire function behaves only as if it was based only on one formula. So the entire function, it's like function based with expressed with a single formula, and so it is continuous. We started that all single formula functions are continuous. Behaves like it is expressed with a single formula, so continuous. And since we previously considered continuity at x equals 5, so it is continuous at x equals 5. Now the same exactly reasoning can be applied to any other x value, like x equals 10, it will be the same, or maybe x equals 0. For x equals 0 though, it will be slightly different. For x equals 0, all the values that we deal with, they're all smaller than 2, and so we'll be using the other formula. But still, we will be using a single formula. It will be the other formula, but it will be a single formula for all the calculations. And so this reasoning still works. The entire function behaves like it is expressed with a single formula, and therefore it is continuous. So same reasoning works for x equals 10, x equals 0, etc., etc. For almost x values, the same reasoning works, and the result works. So the conclusion works. So the function is continuous. However, there is a single x value for which this entire reasoning is not working. And this x value is x equals 2. So let me show you. So now let's pick x equals 2. The difference of x equals 2 from all the other x values is that x equals 2 is actually separating between application of these two formulas. For x values greater than 2, we use one formula. For x smaller than 2, we use the other formula. So reasoning for x equals 2 will be different, and let me show you that. Once again, to check continuity, whether the function is continuous, we need to check the limit formula, but now it's 2. X approaches 2, f of x equals or not equal f of 2. Now I probably need to restore the function itself. So f of x equals x squared minus 3 for x greater or equal to, and x plus 1. So once again, f of 2 is easy to calculate because 2 belongs here. We plug into 2 squared minus 3 is 1, so f of 2 equals 1. But now for this limit, if you try to apply the same reasoning, x should equal slightly bigger than 2 numbers, such as 2.1, 2.01, and slightly smaller than 2, such as 1.9 and 1.99, etc. Now see what happens. When we plug in x equals 2.1 and 2.01 into the function in order to calculate function values, we will use the top formula. But when we plug in 1.9 and 1.99, because they're smaller than 2, we will be using the bottom formula. And unfortunately, it's not the same formula used all the time, and so we cannot use the same reasoning like before, saying that the function is expressed with a single formula, therefore it must be continuous. So, not the same formula used all the time. It does not necessarily mean that this function is always discontinuous, but it just means that the previous reasoning is not working and we need to use a different reasoning to calculate this limit. So what reasoning would we use? And the approach we use will be one-sided limit. So we use one-sided limits. Namely, limit as x approaches 2 plus, and next to it or in parallel we will be calculating limit as x approaches f minus. Now, x approaches 2 plus means that we're plugging in 2.1 and 2.01, etc. Again, I'm not physically plugging them in, but I want to determine which formula I will be using. Yes, I will be using the top formula because those are all bigger than 2. So, for x values like that, we will always be using only the first formula and not the other formula. And therefore, by calculating this one-sided limit, we can treat the entire function like only function expressed with single formula. So we can actually put this formula here. X squared minus 3 as x approaches 2 plus. And now we got limit of a single formula function. And since single formula is continuous, we know how to calculate limits like this. We just plug in. So plug in x, and since x approaches 2 plus, it actually still means that it approaches 2, only it approaches 2 on the right hand side. So it's still plug in x equals 2, and we end up 2 squared minus 3, which is 1. So that's the answer for the limit on right, for the right hand limit. Now for the left hand limit, we plug in numbers like 1.9, 1.99, etc. And for those numbers, we use formula x plus 1. Again, we can argue that this function now behaves like function expressed with only one formula, and that formula is x plus 1. So we can put it like this. X plus 1. Once again, this trick about replacing the entire function with a single formula, it was not working for the two-sided limit, because for two-sided limit we would have to use 2 formulas. But for one-sided limit it works, because for each one-sided limit we only use 1 formula. So for the left-hand limit, we plug in x equals 2, but plug into that formula. So plug in x equals 2, and that is 2 plus 1, and the answer is 3. So we found that the right-hand limit equals 1, the left-hand limit equals 3, and from here we can deduce that since these two do not match, therefore the two-sided limit, which is side, which means we found this limit, and the answer is DNE. The right hand side we found before, and the answer is 1. Of course, DNE is not the same as 1. So left hand side is not equal to right hand side, and so the function is discontinuous. So f of x is discontinuous at x equals 2. And since we have previously determined that it is continuous at all the other x values, so x equals 2 is the only point of discontinuity. So the answer was, the question was to find any points of discontinuity, and the answer is x equals 2 is the only